Welcome to the wasteland. If you are preparing for your Cambridge mathematics examinations, whether that's syllabus 0580, 0606, 4024, 4037, or 4040, you already know the exam paper can feel like an absolute wasteland of tricky, demanding questions. You are navigating this fiery road, trying to claim that A-star treasure. But so many students crash. Take our two example students today. We've got Alex. Now, Alex overloads every answer with raw mathematics facts, but uses zero analysis. And then we have Sam. Sam rushes the paper, panics, and completely misses the command word requirements. They both end up with a page full of red pen marks. Well, today, in this explainer, we are going to fix that. We are treating mathematical functions like machines in a factory, transforming abstract algebra into a highly visual journey, and we're going to arm you with the exact exam strategies you need to survive. Let's get started.
Look closely at your screen. What's really interesting here is how Einstein's formula for success and this everyday fuel pump both perfectly illustrate the exact same core concept we see in Cambridge exams: real-world inputs generating calculated outputs. On the exam paper, the question itself provides your measured inputs, your given data, but the command word tells you exactly how that data must be processed. Are you being asked to find, calculate, or show that? Sam rushes this part and calculates an output the examiner never actually asked for. Remember, mathematics is simply the study of these roles, how one set of data translates into another based on a specific, calculated framework. So here is our mathematics success blueprint. This is our roadmap out of the wasteland. We're going to build our understanding progressively. We'll start with what a function actually is, then we'll decode mappings, learn to reverse engineer these machines with inverse functions, look at how to chain them together into composite functions, and finally conquer the absolute rule of the modulus function. If you stick with me through all 5 of these, those red exam marks are going to turn into green check marks. Okay, let's dive into the core machinery of our mathematical factory. Section 1. What is a function? The basic machine. And as we do this, I want to introduce you to the framework that top Cambridge students use, the PEL framework. Point, evidence, explanation, link. Keep that in the back of your mind as we analyze how these machines work. Here is the fundamental definition you need to lock down. A function acts as a totally reliable, predictable machine. You give it a specific input, and it gives you exactly one predictable output. Imagine a number machine where the first operation is multiply by 2, and the second is add 3. Input a 4, and it spits out an 11, every single time. Now, when Alex gets asked to define a function on an exam, Alex writes a massive paragraph dumping every algebraic rule imaginable. But using our PEL framework, your point is simply stating the rule: one input to one unique output. Your evidence is the algebraic notation, like f of x equals 2x plus 3, keep it precise. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, this brilliantly illustrates our essential vocabulary. The domain is the raw material you can safely feed the machine, your possible x values. The range is the final product it spits out, your y values. When Cambridge examiners ask you to state the domain, they are testing if you know it breaks the machine. If x is in the denominator of a fraction, you literally cannot input a number that makes that denominator 0. Alex usually forgets to state this exception, losing vital marks. Let's move to our next section and see how these relationships, or mappings, can be sorted into distinct categories. This is where we start transforming those flawed answers into top-tier, structured responses. By laying these mapping types out side by side, we can clearly trace the path from the object, which is our input, to its image, which is the output. Look at the table. Mappings come in 4 distinct flavors. 1-to-1 is straightforward. One unique input goes to one unique output. Think of a perfectly straight diagonal line on a graph. Many-to-1 means multiple different inputs land on the exact same output, like a U-shaped quadratic curve, where x equals 2 and -2 both give you a y of 4. Then we have 1-to-many, where a single input splinters into multiple outputs. And finally, many-many, which is a chaotic mix, like a circle graph, where everything crosses over. Now listen closely, because this is the golden rule for your exams. A true mathematical function cannot have a single input splintering off into multiple different outputs. If you press a single button on a machine, it cannot randomly give you 2 totally different products. So only one-to-one and many-to-one mappings actually qualify as true functions. One-to-many and many-many fail the test completely. When the examiner asks you to justify why a mapping isn't a function, Sam usually just writes, "It looks wrong." Don't do that. Use your explanation and link from the Peel framework. Explain that one input yields multiple outputs, and link it back to the golden rule of functions. That's how you secure the marks. So, what happens if we want to take our finished product and reverse engineer it back into raw material? Section 3, Reversing Machines, Inverse Functions. Let's see how we run this factory backwards. To run the machine backward, we need an inverse function. If the original doubles your number, the inverse cuts it in half. But notice a massive absolute constraint here. We can only do this with 1-1 functions. Let's think about why. Every output must have a single clear origin. If you try to reverse a many-one function, like that U-shaped curve where both 2 and -2 resulted in 4, and you feed the number 4 into the reverse machine, the machine would literally panic. It wouldn't know whether to spit out a 2 or a -2. Without a unique path back, the inverse simply cannot exist. Now, what's incredibly beautiful about this, and what examiners love to test, is the perfect symmetry. Because we are quite literally swapping the inputs and the outputs. The domain of your original function becomes the exact range of your inverse, and the range of the original function becomes the domain of the inverse. They trade places entirely. When Alex gets a question asking for the domain of an inverse, Alex tries to calculate it from scratch, wasting 5 minutes. A top student just looks at the range of the original function and writes it down in 2 seconds. Stop scrolling! Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, getting back to it. Visually, this means if you plot a function and its inverse on a graph, they mirror each other perfectly across the diagonal line y equals x. Any coordinate at, say, 2, 5 on the original graph flips to become 5, 2 on the inverse. It's a perfect reflection. Now it's time for our interactive workshop. Imagine a 60-second visual countdown timer right here on the screen. Challenge 1, data scan. When you need to find an inverse algebraically, you must extract the core process quickly. Step 1, let y equal f of x. Step 2, literally swap the letters x and y in the equation. That is the algebraic equivalent of reflecting across that diagonal line we just talked about. Step 3, rearrange to make y the subject again. Sam always rushes this rearrangement step, drops a negative sign, and loses the final mark. Take your time, show your evidence, you're step-by-step working out. Let's dive into what happens when we link several machines together to create a mathematical assembly line. Section 4, composite functions. This is where the exam really tries to trip you up. Okay, challenge 2, find the flaw. I'm going to show you where marks go to die. We write composite functions as fg of x. Sam reads this left to right, processing function f first, then function g. That is a massive flaw. This notation feels backward, but you must always process the function closest to x first. So for fg of x, you must feed x into machine g first. Then take whatever product machine g spits out and feed it directly into machine f. Don't let the examiner catch you reading it the wrong way around. Challenge 3, speed writing. You've got 30 seconds on the clock to write a perfect Peel paragraph explaining this rule. Go. All right, think of it logically. The second machine on your assembly line can only process the materials that successfully made it through the first machine. If a particular number causes the first machine to break, maybe a divide by 0 error, then it cannot physically make it to the second machine. The domain of your combined function is strictly limited by what that first machine is capable of handling. That is your point and your explanation right there. Finally, let's look at a very specific type of machine that absolutely refuses to deal with anything negative. Section 5, the modulus function, the absolute rule. This is a crucial topic for syllabus 0606 and the additional maths papers. Let's think about this logically. Imagine a real-world scenario where negative values make absolutely no sense at all. Like measuring physical distance. If I step 3 meters backward, my position might be -3 on a grid, but the physical distance I traveled is still 3 meters. It's a positive quantity. So how do we represent that algebraically when our standard line graphs regularly dip below the 0 mark? The modulus function is our absolute rule that strips away the negative sign, leaving us with pure magnitude. It's denoted by these straight vertical lines around the variable. If the number inside is already positive, the machine does nothing to it. But if the number inside is negative, the modulus forcefully multiplies it by -1 to turn it positive. So the absolute value of -28 simply becomes 28. Alex often overcomplicates this during exams by trying to square and square root things, but it's much simpler. Just look at the magnitude.
And this brilliantly illustrates why modulus graphs look like they literally bounce off the x-axis. Because no output can ever be negative, any part of the standard graph that would normally dip below that horizontal x-axis is forcefully reflected upwards into the positive zone. This sudden, violent change in mathematical direction creates sharp V-shaped corners on your graph. We call these sharp points cusps. Examiners will specifically look to see if you have drawn a sharp cusp or a rounded curve. If you round it, you lose the mark. It must be sharp.
So, as we wrap up our strategy section, let's look at our progress bar hitting 100% mark potential. Ask yourself this advanced question. How could we slice up a many-one parabola so that a piece of it can actually be run backward? You restrict the domain. You chop it in half at the vertex, leaving only a 1-1 curve that can be perfectly inverted. That is your ultimate mathematics success blueprint. 3 rules to guarantee top marks. Decode the command words like calculate versus state, apply the PL framework to your written logic, and manage your time matrix so you don't rush like Sam or overwrite like Alex. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.